confidence intervals. And the first thing we're going to do is we're going to review the t-distribution. So recall that as the degrees of freedom, which is related to the sample size, so as the sample size increases, the degrees of freedom also increase, and the distribution, that is the t-distribution, becomes more and more normal. In fact, it limits to a normal distribution. When the degrees of freedom are relatively small, and typically that means less than 100, then the t-distribution has a higher probability for large values as illustrated by this green curve. So this green curve has a lot more area compared to the normal distribution for values bigger than 4. Okay. So the question is, what is the t-distribution exactly? So the t-distribution is given by this quantity, the sample average minus the population mean, divided by the sample standard deviation over the square root of n. Okay. Just as so that we can recollect and define all the terms in this, each of these terms is defined here. So S is the sample standard deviation, N is the sample size, the X bar is the sample mean, calculated from the data you collect, and the Greek letter mu is the unknown population mean. Okay, so let's just review percentiles. Percentiles are a quantity, percentiles are the X value that correspond to a prescribed probability. So the percentile of 97.5% or percentile is 2.03. Okay, so we could calculate the probability t-distribution with 35 degrees of freedom is between minus 2.03 and positive 2.03, and we could calculate that probability and see that it's 95%. Now you could use the table in your book, you could use a program such as R, or you could use Python to verify this. Okay. The command in R here is this qt command. In Python it will be different, and you'll need to use the stats package. Okay. So let's consider this example. A random sample of 36 unemployed individuals is taken, and it's found that the sample mean age is 32 years of age with a sample standard deviation of 9 years. I want to calculate a 95% confidence interval for the mean age of unemployment based on these 36 individuals. So we're just going to define all the terms. The sample average is 32 years. The sample standard deviation is 9 years. I have 36 data points, so my degrees of freedom is 1 less. It's 35. The level of confidence is 95%, so in some instances it's useful to calculate alpha and alpha over 2, which is the 2.5%. This confidence interval we can calculate as follows. So recall that we calculated the probability of t-distribution was between minus 2.03 and positive 2.03 is 95%. The t-distribution can be calculated using this sampling statistic. And now we plug in the parameters we know. We know that the sample average is 32. The population mean is unknown, so we'll leave it there and in fact solve for it. We know the sample standard deviation is 9 and the sample size is 36. So if we solve for the unknown parameter of the population mean mu, we're going to get this. And there's one last step, which is to move the 32 to the other side and to make the population mean positive. When we do that, we get this quantity. So the confidence interval will be 32 plus or minus that 2.03 times 3 over 2. We can abstract how we came about this process and come up with a nice little formula to describe a confidence interval on the population mean. And that rule that I tell you to calculate a confidence interval on the population mean would be as follows. Calculate the sample average, add and subtract the corresponding percentile from the t-distribution corresponding to alpha over 2, multiply that by the standard deviation over root n, and that quantity here will give you the confidence interval for the population mean when we have the sample standard deviation. Okay. So here's an example. We want to find a 99% confidence interval for the mean time required for an oil change at a local company. We know that we take a random sample of 30 observations and we compute the sample mean, which is 17.2 minutes, and a sample standard deviation of 6 minutes. So we just write down everything we know. There's the sample mean, the sample standard deviation, the sample size, then we calculate the degrees of freedom, and we find the value of corresponding to the percentile, the t-distribution with 29 degrees of freedom, so that there's 2.5%, or excuse me, so there's 0.5 or half a percent of area in the t-distribution's tail corresponds to 2.756. And then we just plug all this information into that formula, and we get that on average for the population, we would expect the average value to be between 14.2 minutes and 20.2 minutes. Okay, so here we calculated this t-distribution with alpha over 2 degrees of freedom. What does that alpha over 2 really mean? And we'll get to that in just a minute. One thing that I just like to remark is that if you know the standard deviation, you in fact, for some reason, know the population standard deviation, it's much more accurate to use the normal distribution, that z sub alpha over 2. And so if you know the population standard deviation, the formula changes as follows, and the percentile is calculated with this normal distribution. Now, the alpha over 2, it's the amount of area in each tail. The 1 minus alpha is the amount of probability on the interior. So 1 minus alpha is the level of confidence. So 99% means that alpha is 1%, so a 99% confidence interval. 95% means alpha, 95% means alpha is 2.5%, and 95% goes in the interior. And 90% means alpha over 2 is 5%, and alpha is 10%. Okay. Okay. Well, let's take an example here. So here the mean birth rate of preterm newborn babies at a local hospital is 4.8 pounds and a sample of 36. Doctors believe the standard deviation is 3 pounds, and we want to construct a 95% confidence interval for the mean weight of preterm newborn babies. And the first thing we do is we just write down everything we know. We know the sample average is 4.8, the standard deviation is 3, we have 36 observations, we want a 95% confidence interval, and so alpha over 2 is 2.5. Okay, we'll see that z sub alpha over 2 is minus 1.95. So this confidence interval is going to be given by this quantity right here, which we calculate to be between 3.825 pounds and 5.77 pounds. Okay. Now, this confidence interval suggests the upper and lower bounds for the population estimate is between 5.77 to 3.825. But I want to point out what's random, the meaning of this last bullet. What's random is the interval. Okay, the population mean is one fixed quantity. And so sometimes you get a small sample size or a biased data set, or you don't have a large enough sample size. This interval may not capture the population mean and may not always do a good job of giving you the estimate for the population mean. Okay, so the last thing I want to leave you with is a summary of how to calculate confidence intervals. There are two scenarios. If you know the standard deviation, you'll use the top formula, or the more common situation in which you don't know the standard deviation, so you estimate it from the data and use the sample standard deviation, then you use the formula on the bottom. Thank you very much.